Kia ora koutou, no mai, haere mai. Welcome to lesson 35 for introductory physics. This is the penultimate lesson. There's one more after this. This lesson is going to talk about colour. The whole lesson is just about colour and what colour means, what we're defining by colour, how different colours work, how our eyes work, and how we see and interpret colour, and therefore how we can create colour through things like screens, like what you're watching this on, or through printing. So everything about colour. Our goals are to do basically what I've just said, to describe colour as a property of light, how our eyes detect it, state the three additive primary and subtractive primary colours and explain complementary colours, explain selective reflection, selective transmission, explain colour theory behind printing and computer screens, define scattering, which will lead us into why the sky is blue, why sunsets are colourful, and why clouds are white or grey. Then we will introduce a little topic at the end called emission spectra, and that is to do with atoms emitting photons. And very end of the lecture, we'll see us define a few terms. So that last statement is just definition of the terms luminescence, fluorescence, phosphorescence, and incandescence. First of all, though, what is colour? What do we mean by colour? We've already talked about the idea of there being different colours. We explained that when we were talking about different visible frequencies. We said the red end and the violet end. So we've already got this idea that different frequencies are going to be different colours. And that's exactly what colour is. Colours are just agreed upon names for ranges of frequencies of visible light. Different frequencies are absorbed by parts of our eyes, which result in electrical signals being sent to the brain, and they are different signals depending on what the frequencies were that were received. Our brain interprets these different electrical signals as different colours, and our languages have evolved to reflect those different images, those different colours that our brains create. The eye itself, we're not going to go into great detail. I don't expect you to remember all of these terms. I'm not too worried about this part of the eye structure, but I will just include it for completeness, and that is the front of the eye is the cornea. That's where the light travels in through. It travels in through the cornea, in through a hole in the middle of the iris, which is called the pupil. Then the lens, which focuses the light. We'll talk about lenses in the next lesson. And then the light rays, the photons, arrive on the retina. The retina is the inside of the back of the eyeball. So it's inside the eyeball, but it's the lining on the inside of the back of the eyeball. Don't worry about the blind spot or the fovea terms there. We're not going to look into those. I just want you to know that's where the retina is. The retina is made up of two different types of cells, rods and cones. They are both types of cells that absorb photons. That means we call them photoreceptors because they can absorb the photons, but they do so slightly differently. A rod will handle low light vision. It really is just talking about whether there's a photon there or not. It's really just seeing in black and white. Protons, I don't even know what that word was going to be. Rods are in the sort of the periphery. So our very peripheral vision right out the side is mostly handled by rods, and it's actually mostly in black and white. Sometimes your brain will fill in a bit of color based on what it knows. If you start with something here and you move it back, your brain already knows what color that is, so it can keep it that color. But if you had someone that snuck up beside you, as soon as they come into view, they would actually appear black and white to your brain, even though, again, it may fill in some colors because our brains are pretty good at making up for things we don't actually know. So that's what rods are. We're not really going to talk about them much more than what I've just done. That's pretty much it. Cones are the bit we're going to be interested in today. Cones are the things which handle color vision. They're denser towards the center, towards the dominant part of our vision, which is right in front of you where you're focusing, where you're looking. That's where cones are more dominant, and cones have three different types that are stimulated by different frequencies of light. Different frequencies being different colors means cones are how our eyes tell different colors apart. We have three cones. Each one can absorb all the different frequencies of visible light. They can, but they have a region in which they do best. As per this graph here, you'll see that we have a blue cone, a green cone, and a red cone. Again, those are just the names we give them. They don't perfectly align. As you'll see, the red cone is actually quite dominant around the sort of orangey yellow region, but it's also the best one for all of the red colors. Green is the best one around the green colors, and blue is the best one around the blue colors, but you'll see it does drop off towards the violet, bluish, purple end there. So the cones all have different sort of peak frequencies, not peak frequencies that they emit, like we saw with emission thermal physics, but in terms of the peak ones, they absorb best. You'll see the wavelengths written above those three cones. Those again are their focal points, the ones they absorb best, but they will absorb lots of different photons well. You can see blue absorbs anything right from the 400 nanometer up to over 550 nanometers, although it's getting pretty low absorption by then. The green photoreceptor cells, the green cones, they can absorb pretty much the full visible spectrum. But again, by the time it gets to the ends, it's not absorbing very much. Red drops off sort of before the full blue end, so it's not so good around the really blue to violet ones, but can absorb pretty much everything else. When a photon comes in, it's absorbed by these cones. And of course, you never get a single photon, right? So you're always getting a whole bunch of photons. You might get 1,000 photons in a little instant, and that'll get absorbed by a whole bunch of cones. And so one photon might hit a blue cone, which doesn't absorb it too well, and another identical photon might hit a green cone, which absorbs it a bit better, and your brain takes that information and sends it, or your eye takes that information, sends it to the brain. The brain uses that to decide what color it's seeing. So for example, if a violet photon comes in, then it will be absorbed well by your blue cones, but not so well by the green cones, but still a little bit, and not really at all by the red cones. And so your brain will take that information and say, oh yeah, blue, little bit of green, but barely any, and pretty much no red. That must be right at the violet end of the spectrum. If a blue photon comes in, blue cone is still the best. It's not just using that information, it's using all the different ratios. So it says blue's still the best, but now green's actually picking it up reasonably well. And red's still not really picking it up, but maybe slightly more than it was for the violet one. So that's going to be bluer than the violet one was. So our brain sees it as a slightly bluer color. And that's the same for all the different frequencies that come in. That ratio of the different cones and how well they absorb those frequencies will tell your brain what color it is looking at. That is what cones do, and that is how we see color. As a little sidetrack, which is technically getting into philosophy, but philosophy, from my view, is very interesting and worth thinking about for a moment, but not part of the course material. Our cones absorb a photon. Depending on the frequency of the photon, they send a different electrical signal to your brain. That electrical signal is all your brain is getting in terms of visual information. That's it. It's an electrical signal. Right? So everything that you see, the vision that you have, is just your brain processing those electrical signals. It's organizing them and it's presenting them in a visual manner, whatever we mean by that, to you, even though you are the brain, right? So your consciousness can interpret this visual information so that you can understand your surroundings. But that means that the way a color appears to you might be completely different from how it appears to someone else. Right? There's no specific thing in our brain that defines color other than an electrical signal saying this wavelength. So we all agree that a photon that comes in of a wavelength of 700 nanometers is going to be red, but there's absolutely no way to see how someone else's brain visually interprets that red color. So it's a fun little thought experiment to make you realize that no one really knows anything about how anyone else sees anything. All right, so what is white light then? We've talked about the different colors in the rainbow, but what about white light? If all three cones are absorbing photons in equal amounts, so they're all absorbing lots of photons, then that means we must have photons of different frequencies all coming in at once, because that's the only way you can trigger all the cones, and that's what we call white light. White light just means that there's more than one color, and there's enough different colors that it triggers all of your three cones pretty equally. There is no such thing as a white photon. Does not exist. No such thing. It takes at least two different photons to make white light because you need to trigger all three cones equally. So in terms of only two colors, you could look at this diagram and you could say if you chose the right sort of yellowish green, that would give you really strong red and blue, red and green, but not much blue. And then you could choose a quite strong blue one that gives you barely any green and red. And you could add those two photons that would trigger all three cones equally, and your brain would see that as white. So that's what white is. Just means all three cones are being triggered at once. But it's important to remember that white light means multiple different colors of photons, at least two, usually more, at least two different colors of photons all coming into your eyes at once. That's all white light is. Black, what's black? Well, black is just the absence of photons. It means your eyes are not receiving any photons in the visible range and therefore not seeing any color. So white is all colors at once, black is no colors, and then all the other colors are just specific frequencies. When we look at a light source, the photons are traveling directly from your eyes, from the light source to your eyes, getting absorbed by the cones, and because it's a white light, usually it will trigger all three cones, and then you'll see it as being white light. Obviously, if it's yellow, then it's triggering the yellow parts of the cones, well, the right combination to make your brain think it's slightly yellower, and you can get bluer lights, which are slightly bluer and so on. But in general, for a white light, it's going to be triggering all three. So it's just sending a whole bunch of photons out. They travel straight from the light source to your eyes, get absorbed, and your brain says, oh, there's this thing producing white light over there. So that's when we observe light directly from a source. But what about when we look at something else? If you look at the wall or the chair or your desk or a bit of paper, that's not producing photons. That's not creating visible light. So where are those photons coming from? If everything created visible light, we wouldn't need light bulbs, right? If everything just created it, we wouldn't need light bulbs. So what's happening is that the visible photons created by the light source, whether it's a light bulb or a sun or whatever you're using, they are reflected off everything else in the world, right? All the other surfaces reflect it. So when you look at the wall, what you're seeing are photons being reflected by the wall, but those photons came from the light bulb or from the sun or from some whatever light source. So that's how you see everything else in the world. So you see light sources because they emit a photon, you see everything else because it reflects a photon. So when you see photons from a surface, generally, most surfaces will reflect photons in every possible direction. And so you're only seeing some of the photons that they reflect, as per this relatively messy diagram. In this diagram, the light bulb is still sending photons everywhere. Some of those hit the book, and when they hit the book scatters them off, it sends them off in all these different directions. And some of those will hit your eye. And when they hit your eye says, oh, that photon came from there, so that thing must have reflected it. We'll talk a bit more about how we interpret the color of it shortly. But that's how we know there's an object there, because there's something there that has reflected that light towards your eye. If it reflects all of the photons, so white light coming in from a light bulb or the sun, if they all get reflected off that object, it will appear white. So if I hold up a piece of white paper, that only appears white because all of the photons from the light above me are coming down and hitting this paper and then being sent off in every direction, but they're still all being sent off. So when you look at it, you see photons of all different colors, and therefore it appears white coming off that paper and arriving at your eye. So white objects reflect all color photons. If they reflect no photons, then there would be no photons coming from that location in space. So if I hold up something that is black, then there are no photons. There are still photons hitting it from the light, but none of them are bouncing off it towards me, and so it appears black. Right? So that's all black and white are. Black is not bouncing off any of the photons, it's absorbing them all. White is bouncing off all the photons, so you see white. In reality, of course, we still see black objects, we still see detail in them. So they must reflect some photons, otherwise our brain would have no information to go off. So in reality, most black things are actually a kind of a dark grey. They are reflecting some photons, but very few, so our brain says there's not many photons coming from there, it must be pretty much black. right? But there's still enough photons for our brain to build a bit of a picture about what that object does look like, such as that black cat. You look at that black cat, you can still see where the hairs are and where the curves are, even the bits that are mostly black. So you look at the cat's nose, it's all black. The surrounding hair is all black, but you can still tell where the textures change and things because there is some light coming off of that part of the cat. A true black will absorb all photons and reflect none, involving absolutely no visual information for your brain to interpret. And recently, we've got new technology that is creating blacker pigments than we've ever had before that absorb more and more light. They're up to over 99% of light being absorbed. That photo there is an actual photo of two identical masks, but one has been covered in a black pigment called Vantablack. It's not technically a paint, it's a special type of material, but it's sort of applied in a similar way to paint. And that is an actual photo, and you can see there are just no photons at all coming off that black painted mask. So it just looks like this black void, the space, as if there's nothing there. So a black object, in everyday language, we're talking about black, we're talking about something that's giving off very few photons, so we think it looks black-like, whereas real black means no photons at all, and you get nothing, no information at all. So there's just a little bit of clarification there. What about everything else? What about all the things that aren't black or white? If an object is better at reflecting some frequencies than others, then our eye will see it as being that color. So if I hold up something that's any other color, right, this red pen is better at reflecting red photons than it is at reflecting any other color of photons. So the photons that arrive in our eyes from this pen are mostly red, so we see it as a red pen. And the same for any other color. Whatever color it's better at reflecting is the color we see it as. Again, just like black, it's not going to be perfectly absorbing every other color and only reflecting red. And of course, red isn't a single frequency. Red is a whole range of frequencies. So it's all a bit wavy and not really precise, but it's still always true that a red thing will be reflecting more red photons than any other color and absorbing most of the other colors and not reflecting them. So that's how we can tell what color an object is. If an object reflects all frequencies, it appears white. If it reflects all except one, it appears as the inverse or complementary color, which we'll talk about in just a moment. If it reflects a specific color range, like the red one, then it will appear that color. Right? Or if I hold up a blue one, it'll appear blue. Right? It's reflecting most of the blue photons and not many of the other colors. If I hold up an object that reflects very few photons, right, that's going to appear black. So that's all that we are interpreting when we look at different colors. What kind of frequencies is that reflecting best? We already talked about transmission as well, the idea of glass being transparent to light. It lets visible photons through. If it's clear, like standard window glass, it lets all the frequencies through. But of course, we can get things which only let some frequencies through. So we can make colored glass or colored plastics. And that's the exact same process as the object appearing a certain color, except that now it's talking about transmitting a color instead of reflecting it. But it's the same principle. If you have a blue piece of glass, that means it's absorbing most of the other colors of frequencies, but it's transmitting blue photons pretty well. And so the blue light will get through and not much of the other colors will get through. The object or the window, the glass will appear blue. So now we've got an idea of what we mean by objects being different colors. It just means they reflect or transmit certain ranges of frequencies better than others. And we've got an idea of what colors are, and that's just different frequencies that our brain interprets different ways. So now we're going to start talking about additive color. And this is the idea of using different lights. And this will build us up to computer screens and things like that. So additive primary light colors are the colors that our cones are set to receive, the red, the green, and the blue. So red, green, and blue are the additive primary light colors. Those of you that have learnt the primary colors through school or through art will probably be thinking red, yellow, and blue are the primary colors. Those are the artistic primaries, although even those are not technically correct for any primary anyway, but they are The primaries due to historical availability of different color pigments and through simplicity of primary school education. They are in no way primary in any scientific sense. So in science, we have additive primaries, and we'll meet subtractive soon. But additive primaries are red, green, and blue, because those are the three colors of our cones, right? Red, green, and blue, the three different colors that our cones focus on. Well, focus is a bad word, given we're going to look at lenses in the next lesson. But anyway, because of that, because the way our cones work, we can trick our cones. We can trick our eyes into thinking there's a color there that isn't. If we shine a green and a red light at the same time into our eyes, then it will trigger our green cone and our red cone. Right? And if we shine a yellow light into our eyes, it will also trigger our green cone and our red cone. So our brain cannot distinguish between the signal it gets from red and green light simultaneously versus yellow light. Right? It can't tell the difference. They do the exact same thing. You look at that diagram, right? In green and red, you get a bunch of green, you get a bunch of red triggered, you get a little bit of blue triggered. If you get yellow, then you get equal amounts of red and green and a little bit of blue triggered. So they are very similar. And if you shine red and green at the same time, your brain will simply see it as yellow. So if you have a red light and a yellow light, red light and a green light, you turn them both on, it will appear yellow. That's why we call them additive primary colors, red, green, and blue, because you can add them to make all the other colors. You add them together to make other colors. This diagram here is an example of that. If you add them together, then you can produce any color in the spectrum. The red and the blue, when they overlap, they will cause a color called magenta. Red and green will appear to be yellow, green and blue will appear to be cyan, and if all three shine at once, you're triggering all three cones, and that's what we said white was. So you can get white light. One of the additional resources for this lesson on stream is a link to an O-Physics, I won't say simulation, more of an activity where you can play with an image that looks just like this, and you can change the intensity of each light, say how much red, how much blue, how much green there is, and see what different colors are made. And you can make any color you choose by finding the right combination of red, green, and blue. And of course, that's how computer screens work. So you will be familiar, if you've ever done any computer work with colors, you'll be familiar with that. Because what's happening is that every pixel on a computer screen, so a pixel is the smallest little square that the image is broken up into, has three tiny light sources, a green one, a red one, and a blue one. And it turns them on at different amounts. And so this GIF here is zooming in on the center of this red diamond. And if you watch carefully, you can see that most of the pixels, most of the areas around that center spot, the red pixel, the red part of the pixel is a bit brighter than the green and the blue parts. But right in the very center where we've got that little white sort of reflection, so when it zooms out, you'll see there's a little white bit in the center there. As it zooms in, you'll see that all three colors, red, green, and blue, are all equally bright in the center. But when it zooms out, it just appears white to us. That's what white is, right? It's all three colors at once triggering our cones, thus appearing white. And that's how digital displays work. They have three different colors built into them in tiny, tiny little pixels, and they all turn on and off accordingly or at different intensities to create all the different colors. So every color that you have seen, every color right throughout all these videos that you've ever seen on any screen is all coming from just red, green, and blue light sources. That's all they are. Subtractive color. I mentioned this word just before, so what are we talking about with subtractive color? Every cone has a dominant color. When we miss out one cone, rather than two, if you just trigger one cone, you're missing out two. But what happens if you trigger two cones and miss out one? Then you get a subtractive primary. They're called subtractive because it is white light minus one of the additive primaries. So if you have white, but you take away the red, that means you're still triggering the blue and the green, and that gives you cyan. As we just saw, if you shine blue and green light together, you get cyan. If you shine red and blue, that means you're missing green, you get magenta. If you shine red and green, you're missing blue, you get yellow. So cyan, magenta, and yellow are the subtractive primaries. Subtractive primaries are the ones that are actually slightly closer to the primary school colors, as you'll see if I hold up. Now these are not perfectly cyan, yellow, and magenta. They're the closest colors I had in terms of Sharpie pens, but these you'll see they're sort of similar. We've got yellow, and we've got a type of blue, but it's sort of a pale one, and then we've got a pinkish color, which is not too far off red. It's actually magenta. Again, not a perfect example because those are just the colors I had available. So the idea of selective reflection is that an object will appear the color that it doesn't absorb. That means if we have something that only absorbs red, if it only absorbs red, then it reflects all the other colors. That means it'll still trigger our green and our blue cones, and it will appear cyan. So that means that this pen is only absorbing red. It's reflecting the green region and the blue region pretty well and appearing cyan to us. Right, so that's what cyan is. The same thing with yellow. Yellow is absorbing all the blue, but it's still reflecting the red and the green. So this is reflecting all the reds and the greens and appearing yellow. In reality, of course, it may just reflect the yellow region rather than the reds and the greens, but it could reflect all of them. It gets obviously complicated. And magenta being the last one. When you take a color and you add another color to it that creates white, we call those two colors complementary. So if you've got magenta light, that means you've got red and blue, and if you add green light to it, that's going to give you white. You've got yellow light, that means you've got green and red. If you add blue to it, you've got white light. So that's all complementary means. Complementary means what color do you need to add to this light to make it white light. So we're always talking about adding when we talk about complementary. And the subtractive primaries are the complementary colors to the additive primaries. It can be tricky to remember these different colors. Some people like to do the diagram on the left there, which is sort of complicated to do, but you get the hang of it if you try it a few times. And the way that works is you've got the three primary additive primaries in the middle, blue, red, and green. And around the outside, you've got the three subtractive primaries, and the subtractive primary is the complementary to the one opposite, but it's made of the two next to it. So you can see that way. Blue is complementary to yellow. Yellow is made up of red and green, and so on. So you can work your way through that. You may also want to just remember this mnemonic: buy your granny mini raincoats. That's listing the primary and the complementary subtractive to the additive after each other. So buy your is blue, yellow, BY. GM, green, and then magenta, and RC, red, and then cyan. So it's listing each primary and then complementary, or you may come up with a better one. And if you do, please let me know. I'm not a huge fan of that one, buy your granny mini raincoats. So when we talked about a light bulb, a light source that was red and green and blue, and we add them together, we create white. When we're talking about the subtractives, we're talking about the sort of the opposite process. We're talking about starting with white light and taking some colors away. So if you start with white light and you put down magenta paint or magenta ink from a printer, that's only absorbing green. It's reflecting blue and red light. Right? So it's talking now about taking colors away from white light. That's what ink is. That's how ink and paint work. Yellow paint only absorbs the blue, reflects the green and the red. And cyan, obviously the last one, is going to absorb the red and reflect the green and the blue. If you mix two of those colors together, then the substance that's left will absorb the two colors that each one was going to absorb anyway. So if you mix magenta and yellow, magenta absorbs green, yellow absorbs blue. If you mix them together, you're now going to absorb green and blue, which means you're only going to reflect red. So if you mix magenta and yellow together, then you get red. So ink and paint work by adding together these different subtractive colors. And by subtracting more colors from white, you can change the color that you see. And that's how printing works. That's why our printers use yellow, magenta, and cyan inks. They also use black. You could get black by printing all three different colors. If you print magenta to absorb green, yellow to absorb blue, and cyan to absorb red, and you print them all, you're absorbing all three colors, then you get nothing reflecting. You're going to see black. So that's one way to get black, but you can also just use a black ink, use something that does absorb all the colors. And so that's what printers do because it is more cost effective. But regardless, yellow, magenta, and cyan can be used to create all the different colors. Example here, if we want blue, then we need to absorb both red and green. That means we need to print cyan, which will absorb the red, and magenta, which will absorb the green, print them both in the same place, leaving only blue to be reflected, and that will create a blue part of the image. We have to make sure that the printer doesn't put any yellow ink there, because if it did, that would absorb the blue, because that's what yellow does. Yellow absorbs the blue. So if we print cyan and magenta, then we're left with blue. An example here, if you look at this photograph, what it's got is it's got the three different color layers: the magenta layer, the yellow layer, and the cyan layer. And then it's got, for part D, it overlays them all. It also adds part E to create some of the black areas, which you'll notice the photo on the left, part D, doesn't quite look right. That's because it's just the color of each area, not how dark it is, not how shaded it is. So that's what the black is adding in there. We could have obviously, again, recreated that by just printing more of each color at the areas we wanted it darker, but again, it's more cost effective to add that black layer in. But this is a good photograph to spend a bit of time looking at. Look at the different balloons, look at the colors they are down in the bottom row of pictures, and then look at the three different color profiles up the top. That big green balloon right in the center at the top of the photograph, big green balloon. If you look at magenta, that area is almost completely clear. There was very much no magenta being printed, very little magenta being printed there. If you look at the yellow image though, that same balloon is pretty much solid yellow, and on the cyan image, pretty much solid cyan. And that's because, as we said, right, the yellow will absorb the blue, the cyan will absorb the red, and the magenta though would absorb the green, and we don't want that. So by printing just the yellow and the red, the yellow and the cyan, we reflect the green. We are not absorbing the green, and we get a green balloon resulting. And that's how printing works. Again, there's another OPhysics little activity, an interactive image where you can play with the color gradients for this kind of printing as well. A little note on magenta. We've been talking about magenta a bit. It's that sort of pinkish color. It's the idea of your red and your blue cones both triggering, but not the green cone. Magenta is an extra spectral color. That means it does not appear in the color spectrum. The color spectrum goes from red through orange, through yellow, through green, through palish greenish blue, through indigo and violet. It goes through all of those colors. Magenta is not on there anywhere. And magenta isn't just pink. It's not just a light red. Magenta is an extra spectral color. It is so called because, as I said, it's not on the spectrum. And that's because there is no single frequency that will trigger red and blue cones without triggering green. If we go back a whole bunch of slides to our cones, there we go, to this, right, there are some photons that will trigger both red and blue at the same time. You can see them around the 510 nanometer mark. They'll trigger red and blue, but they also trigger green a lot more. And so those are green photons, and our brain sees them as green. It does not see them as magenta because green is being triggered too much. So if you send a red and a blue photon to your eye, then you'll trigger the red and the blue cones, right, more than you trigger the green. You won't get as much green, and that's what our brain sees as magenta. But it's not there is no single photon. So this diagram here was talking about how we could take red and green, add them together and make a yellow. Right? There is a yellow photon. We could just send a yellow photon into our eye and get the same color. There is no such thing as a magenta photon. We could not do that with magenta. So that's just, again, another little interesting thing. It's just another fun fact. Scattering. Next part is scattering. When we talked about transmitting light, the photons traveled through the material, so that means they just kept going in the direction they were going, with a little clarification that we'll actually talk about refraction or bending of light in the next lesson. But in general, they'll just travel in a straight line through the material. Sometimes that doesn't happen. Sometimes the photons are bounced around by the objects, by the particles, and get sent off in different directions. That is called scattering. So scattering is just the idea that if you've got a little molecule or an atom, and a photon comes along, and the photon tries to go through the atom or molecule, that it might instead sort of get bounced off at a funny angle. That's all scattering is. What's the point of scattering? It's going on all the time. It's happening in our atmosphere constantly. Remember, visible light is coming from the sun and it's hitting our atmosphere, which is made up of heaps of molecules and atoms, which are the gases that are filling up the atmosphere, or that are the atmosphere. How much a particle scatters photons depends on the sizes of the particle and the photons. Oxygen and nitrogen molecules are very small. They're tiny little molecules. Blue and violet photons have very small wavelengths, and they will be scattered by these oxygen and nitrogen molecules quite a lot. Red wavelengths are longer, and because they're longer, they actually don't care as much about the little the little oxygen and nitrogen molecules. But the blue end of the spectrum, they're smaller wavelengths, they're similar sizes to these molecules, and they do care about them, and so they get scattered more. So the oxygen and nitrogen molecules, they scatter blues and violets much more than they scatter reds and oranges. They scatter the blue-violet end of the spectrum. They don't scatter the reds and oranges or the greens as much. What does that mean? It means if we look at the sun is actually emitting white light. It's emitting white light, but we depict it as yellow. Why do we do that? It's because that white light is traveling to us through the atmosphere. And as it travels through the atmosphere, the yellow part, that is the reds and the greens and the yellows in betweens, all of those bits of light, all those frequencies, they will pretty much still travel straight towards us from the sun. So they get to us undisturbed. But all the blue photons get scattered away. They get scattered away by the atmosphere. As the white light tries to travel through, all the blues get scattered off in other directions, and leaving all the greens, yellows, and reds to continue on their path and get absorbed by our eyes. Right? That means that the sun is going to look yellow because we're triggering the reds and the green cones, not the blue cones. The sun looks yellow for that reason. So if you look at the sun, please don't. If you look at the sun, again, don't do that. It will appear yellow. It's not actually yellow, but it will appear yellow if you look directly at it. Please don't look directly at it. So that's why the sun appears yellow, and that's why we depict it as yellow in stories and children's paintings. Right? It seems yellow to us because those are the only color photons that get to us through the atmosphere. Indeed, if you go out to space and you look at the sun, it's white. It's not yellow at all. The sun is white. The sun emits white light. The sun emits all the frequencies in our visible range. Again, that's why that's our visible range, because we evolved with the light from the sun. The blue photons from the sun are still here. They're still on Earth. Right? It's just not coming directly to us from the sun. So the sun looks yellow, not white. Where are those blue photons? If they're still here, where are they? They're everywhere else. Right? They're not directly at you from the sun, but they are coming at you from all the other parts of the sky where they've been scattered away from those photons that were traveling elsewhere. So the sun might send a photon over here, but it scatters this way, and you end up seeing that. So if you look at this bit of the sky, you're only seeing the blue photons that got scattered away from that light. And if you look at the sun directly, again, please don't, then you will see the yellow photons. So the sun appears yellow, right? But really the sun is white. You're just seeing the yellow photons because that's all that makes it through the atmosphere. And the sky everywhere that the sun isn't appears blue because that's the blue photons that have been scattered away from the light traveling in those directions. Because it's the particles in the atmosphere that determine how much these blue particles scatter versus blue photons scatter versus the other photons, the atmospheric conditions can affect how blue the sky appears. If we have larger particles like dust or water molecules, then they can scatter more of the other frequencies, more of the greens, yellows, and reds. And the more of those other ones you scatter, the paler the sky becomes because it's getting closer to white light. Right? If you've got all three colors, it's white. If you've got mostly blue but a bit of the other two, then it's going to be a paler blue. It's going to be blue plus almost some other stuff to make it white. And so the more of those other things there are, the more dust and the more water molecules there are, the paler the sky will appear to be. And that is why the sky can often be different colors. So a really dry, clear day with no dust in the sky, if it's nice, fresh, clean air without much pollution or water vapor, it will appear a deeper blue than if it's got some extra stuff in it. What about sunrises and sunsets? It's still the same idea. But now what we're getting is that the sunlight has to travel through heaps of atmosphere. Right? When the sunlight has to travel directly down to us during the middle of the day, it's only traveling through the atmosphere. And please note that this diagram is nowhere near to scale. The atmosphere on Earth is tiny, tiny. It's really thin compared to the whole Earth. If the Earth was the size of a basketball, the layer of water on it would be like really thin. You'd barely even notice it. It's so tiny. The atmosphere is really small. So the atmosphere that the light is traveling through is really small compared to if it's nighttime or sunset rather, and the light has to travel through a whole bunch of atmosphere. Then as it travels through that, that's a lot more chance for all of the particles to get scattered around, not just blue. And that means that the sunlight that's going over here, over to the sides, is you're going to get more of that scattering towards you, more of the reds and greens and things being scattered towards you as well. So you get all these different colors coming through. So it doesn't just appear white, but you get all these different colors, right? So it's the same phenomena. Determining the exact colors obviously gets a bit more complex, but it's the same phenomena occurring. Clouds. Clouds are white. What does white mean? It means we're getting all the colors. We're getting all the colors from the sun being scattered well, right? And that's because water droplets vary in size. There's no one size for a water droplet. So the smaller droplets might scatter more blue light, just like we saw with the particles in the atmosphere, but you also get slightly bigger droplets, which will scatter some green, some bigger ones for yellow, some bigger ones for red. So they scatter all the colors. So water droplets and clouds are a whole bunch of different sizes. They scatter all the colors, and therefore we see white light. We see all the colors that are emitted by the sun. That means that the clouds are actually the color of the sun. We look at the sun, we see yellow. We look at the clouds, you see the actual color of the sun. Clouds are white because they reflect all the light from the sun. Therefore, if you look at a cloud, you are seeing the color of the sun. All right, so that's a fascinating little tidbit of information. What about grey clouds? Well, grey clouds are just because they've got some bigger water molecules, and that means that they start absorbing some of the light. They're not transmitting or scattering it all, right? They're absorbing some of it. As they get bigger, they absorb more. By the time they get really big and really dark, the droplets are quite large, and once they get too big, they will turn into rain. So the darker a cloud is, the closer it is to being a rain cloud. And now we're going to look at a slightly different topic. So that's the end of the color section, the scattering section, the printing, and the light colors. This is still going to be talking about colors, but we're now going to go back to this idea of atoms and electrons in shells. So remember that electrons occupy levels around a nucleus. They are specific steps that the electron can be on, essentially. The higher level is further from the nucleus. The electron needs more energy. It's like a spring. Remember, electron negative being attracted to a positive nucleus. Pull it further away, you need to give it a bit more energy. So the further out the electron is, the higher energy it is. When it jumps back, it gives off that energy. We saw that when we talked about X-rays, and indeed just visible photons as well. The levels around each atom are discrete. That means the electrons have to be exactly on one of the levels. They can't go somewhere in between. Just like we can't stand in between two steps on a staircase, the electrons cannot go, in between two electron levels. They have to be exactly on one or the other. And furthermore, the electron, actually it must be on the next slide. Okay, this slide is talking about the electric potential energy, higher energy to go up to a higher level. When it jumps back down, it gives off the energy. When the electron gets the energy and moves up to the higher level, we call it an excited atom, right? It's excited because it's got a bit more energy, so similar word usage to everyday language. It's excited, got more energy. When it jumps back down, it gives off a photon. That photon will have the exact amount of energy that the electron lost by jumping down a step. And that exact amount of energy will correspond to an exact frequency of photon, because we know from the Planck-Einstein equation that every single photon of a certain frequency has an exact amount of energy given by hf. And so if you have some amount of energy that's becoming a photon, the frequency must be given by that same equation, right? E divided by h would tell us the frequency. So we've already met that equation, and it still holds true. I feel like I've missed a, oh no, it's the next one. Okay. Thought I'd missed a slide, but it's in the next one. So neon lights, you'll see neon lights outside shops and things. That's how they work. electrons are boiled off an electrode inside the glass tube. Don't worry about that aspect of it, but essentially we get these electrons that get fired through the tube, right? Through the tube, which is full of gas. When the electron hits an atom, part of the gas, in this case neon, right? When it hits a neon atom, it gives that neon atom a bunch of energy because the electron's fired, it's going really quick, it's got a lot of kinetic energy, collides with the neon atom, gives the neon atom some of that energy. But the neon atom takes that energy in the form of an electron going up a shell level, up an electron level. It gets excited. The electron has now lost a bit of energy, but it can still keep going, and it finishes the circuit, going back to circuits. But the neon atom is now excited. And that means that the electron has to get de-excited at some point. It has to go back down. It can't stay there. It has to go back down. When it does go back down, it emits a photon. So in this way, neon lights turn electrical energy into radiant or light energy. It's just one way that we can create light. Incandescent bulbs, we'll talk about at the end, but you've already met the idea of something being hot and giving off light, like the sun, that radiation being a result of heat can be visible. But in this case, it's radiation as a result of an excited atom, which is caused by the kinetic energy of a collision with an electron. But, and this is the bit I started to talk about before, the atom levels, the energy levels that the electron can take is determined by the properties of the atom, essentially by how many protons there are in the nucleus. Right? Because the different number of protons, different electrons, there'll be different sort of safe spots it can get to. We're not going to get into why these levels exist, just that they do. There are different levels that are determined by the atom itself, by the properties of the atom. So different atoms will have different sets of steps, different electron levels that it can jump between. And that means the amount of energy it can give off as a photon is different for each different type of element because all those levels are different. So the set of wavelengths that a specific element, sorry, tripping over my words a bit, specific element can emit are known as its emission spectrum. And every element has a unique emission spectrum because every element has a unique number of protons. So it's got a unique format, a unique set of energy levels for the electrons, and therefore a unique emission spectrum. Here are some examples. Obviously, there are a lot of elements. These are just a few. Hydrogen, you can see it's got 4 or 5 sort of purplish wavelengths it can give off, a blue one, a cyan one, and a red one. Helium's got more steps it can give off, and that's not surprising. It's got 2 protons and therefore a couple of electrons in general, so more shells than it can work with. And it's got some similar purple ones, but they're all slightly different if you look at them. It's got a couple of blue ones and then a sort of a paler blue one, a couple verging into the green, a yellow one and a red one, and so on. Neon, you can see that's got a big cluster around the sort of the orangey region. Sodium's just got 3 in the visible region, a greenish and then a couple of yellowish ones, and mercury's got a few spread out. So they're all different, and the visible photons that they can give off, as I said, are unique for each atom. So you can tell which atom is in a substance by seeing which of these photons it actually gives off. Actually, before I go on to absorbing photon, I'll just mention that this is a very well used tool for astronomers. They look at distant stars and distant planets and things, and they can use this sort of information to figure out what distant things are made of based on the photons that they see from it, because we know that certain sets of photons can only come from certain elements. Right? Not true for the stars. Like I said, the stars can give off lots of photons because they're all very hot, but for other types of elements, other types of excitement, then it's these spectra that tell us what photons come off it. There are many ways an atom can become excited. As we saw, you can hit it with an electron and it could get some of the kinetic energy and use that to excite the electron. So there are different ways they can become excited, but one of the ways it can do it is by absorbing a photon. But the thing about photons is that they can't be split up. You can't just take part of a photon. You either take the whole photon or none at all. So that means that for an atom to use a photon to get excited, that photon has to have exactly the right amount of energy for the electron to jump up one level. Right? And the amount of energy for it to jump up that one level is the exact same amount of energy it would give off if it jumped down that level. And given we know that E equals hf, if the amount of energy the photon had absorbed was the exact same amount of energy as the photon it emitted when it jumped back down, then the photon it absorbed must have been the exact same frequency as the ones it would give off. Right, so that means that an atom can only absorb photons of the exact same frequency as the photons that it could emit. So those emission spectra that tell us the colors that an atom can emit, they're also the exact colors an atom can absorb. And that means that if you have an unknown gas and you shine white light through it, so white light being all the colors of the rainbow from the sun, the full white light set, if you shine that light through it, then only the colors that it can absorb will be absorbed. And so if you put something on the other side to measure which colors are coming out of that gas, you will see white light, but with a couple of little black spots where those frequencies, those exact frequencies, have been absorbed by the atom. And that's what you'll see here. So the top one is the continuous spectrum. The next one is the emission. So that's saying whatever atom this is, those are the colors that it can emit. If you instead shone white light through that gas, rather than using the gas to make light, you shone white light through that gas, then it would absorb those exact same colors. Right? And so then the person standing on the other side would see white light minus those exact colors, and that's called an absorption spectrum. And to be fair, that's actually the thing that is used more in astronomy, because they look at stars that give off white light, and then they look at the colors that are missing after that light has traveled through other things out in the universe. The very last part, as I promised, is a couple of quick definitions. So there's not a lot to this section, not a huge amount to memorize, but just some familiarity with a few terms. Incandescence. Incandescence is the idea of light being emitted as a result of high temperature. We've already talked about it with thermal radiation, and it's also how filament style light bulbs work. So you know the old style classic light bulb that's got a couple of little prongs with a tiny wire between them. That is an incandescent bulb. They work by making that little filament really hot, and therefore it gives off a whole bunch of visible light photons the same way the sun does, because it's very hot. So incandescent light bulbs give off a whole range of photons, a whole frequency, the whole spectrum, just the same way that our sun does, but the exact color will depend on the exact temperature. So those often look sort of yellower, because remember, blue photons, higher frequency, higher energy, and red photons, lower energy. And so the cooler it is, the more red it will appear. Fluorescence is the idea of an electron being excited, but being excited by a high energy photon, like a UV photon, being excited up a couple of levels at once, and then jumping down individual levels. And so it might absorb one single UV photon and go up 2 levels, but then it would give off 2 visible photons on the way down. It would step down one step at a time. And so in that way, we can turn UV photons into visible photons by getting them to be absorbed by a specific atom that absorbs them, and then being emitted as visibles. That's how fluorescent light bulbs work. So fluorescent light bulbs use a gas like mercury to create ultraviolet light, and then they have a coating on the inside of the bulb, inside of the glass. That's why fluorescent lights, when they're off, just look like a white tube. It's because the inside of that tube is covered in a fluorescent coating. So the UV light that comes out of the mercury is absorbed by that fluorescent coating. That fluorescent coating goes up at least a couple of levels in one jump, and then goes down in single steps, giving off visible light. So technically, that mercury gas, the fluorescent light bulbs, are creating UV light, but they've just got a coating that turns that UV light energy into visible light energy, so that we can use it as a light source. Phosphorescence is the exact same idea, but it includes a delay. The same idea as absorption and emission in general. So not just fluorescence, but the same idea as absorption and emission in general, but it includes a delay. And that means that the atom stays excited for a while. That's not very common. There's only some materials that do it, and generally it's very quick. The delays are only a few seconds, but there are some materials, again, that we have found and manufactured that can retain that excited state for a long period of time, sometimes up to hours, usually a lot shorter. It's hard to get the ones that last a long time. And all that means is that the material will absorb the photon, and then emit it later on. So you can put something, a glow-in-the-dark item, under a light source, right? Let it absorb a bunch of the photons, and then take it away from the light source, put it in a dark area, and now it will be emitting those photons. Right? So it's still the exact same energy that it absorbed from the light source. It's just got this delay so that you can bring it around and glow somewhere else. There are, of course, other ways to get light. We're not going to go into any detail. Bioluminescence, as it sounds like, is biological. It comes from creatures creating light sources, things like glowworms or fireflies. They use biological processes to convert chemical energy into emitted photons. I've said the word somehow in that slide. That's because these processes are not well understood. They are an area of active research. And if that interests you, then there is certainly research opportunities in that field. Chemoluminescence is chemical reactions producing visible light, such as those occurring in glow sticks. So glow sticks have a tiny little glass chamber with one type of chemical in it, inside a fluid of a different type of chemical, and when you break that little glass chamber and the two mix, the reaction gives off visible light. The last one is a fascinating one that I personally do not know a lot about, sonoluminescence. It is when the sound waves are used to collapse bubbles in the exact right conditions, in the exact right liquids, that the bubbles as they collapse actually emit light waves. I don't know anything about that. I've just heard of it. It's fascinating. You can find videos of it online, but they use sound waves and bubbles and somehow convert that energy into photons. And branching over all of that, luminescence as a term simply means giving off light. So all the different types of things we see are different types of luminescence. So phosphorescence, fluorescence, etc. They're all types of luminescence. And that's the end of this lesson on colour. Obviously a little bit on light production as well and how that relates to different colours. But that is the end of our penultimate lesson. We have one lesson left, and in the final lesson, we will talk a little bit about some optical phenomena.